Chapter 4, Section 3, Part 2 is going to be about non-linear functions and the different kinds and how to find them and write them. So yesterday we talked about telling if something was linear or non-linear, and we learned a little bit about writing linear functions. But today we're going to learn about the other many forms of functions. Okay, they all have what we call a parent function. And that's like the base function before you add anything to it. This is one possibility. This is linear. All right, these are also possibilities. This one, and there's actually another one that looks like this. And we're going to learn about those three today and how do you know which one you're going to use. All right, so let's start with just a little review and some hints on how to know and write a linear function. The equation for a linear function, which means it's going to be a straight line graph, means it could go this way, it could go this way, it could even be horizontal, but it can't be vertical. Okay, that graph is going to look like a straight line. The equation is going to look like y equals some number times x plus or minus some number. Here, we'll make it a number sign. Okay, I actually kind of like it with spaces instead so we don't get confused. Okay, you maybe have seen this as y equals mx plus or minus b. Okay, that's what you're going to do with a linear function. And in order to figure out if you're going to use a linear function, you would be looking to see if they have a constant rate of change. So that it's changing by the same amount every time. And we like to call this our first difference. And I'll show you why. All right, here's an example. I'm looking to see, just like we did yesterday, how it's changing on each side. And it looks like the x's are all changing by adding 1. The y's, looks like here we're adding 5. From 2 to 7, I add 5. 7 to 12, I add 5. Okay, and it appears that that's the case all the way through. So I know that I'm changing by a 1 and a 5 every time. Okay, my y over x would be my rate of change. So 5 over 1 means I'm changing by 5 every time. Okay, so when I'm writing my rule, I'm going to use one of these. For sure, I know that this one's going to work. Okay, so y equals 5, because that's my rate of change, times x. All right, now to see if I need to add or subtract anything, I need to plug in some of these numbers. So let's start with the first one. If I plug a -3 in for y and a 0 in for x, does that give me the true answer? 5 times 0 does not equal -3, but I need it to equal -3. So what would I have to do to this equation? Would I have to add something on or subtract something off to make 5 times 0 equal -3? Well, if I subtracted 3, since 5 times 0 is 0, and I need to get to -3, I could subtract 3. Now I'm going to pick a different set and see if it works for that, because we already know it works for the first one. So 2 equals 5 times 1 minus 3. If I do 5 times 1, I get 5. Subtract 3, that gives me 2. That works. I would check another one just to make sure. So 22 equals 5 times 5 minus 3, and that one also works. So this is going to be your linear equation for this particular table. All right, then we're going to move on to nonlinear functions, and there's 3 kinds that we're going to talk about. This one, the first one here, is going to be called our quadratic. Okay, I like to write it more like this, because this is what our graph will look like for quadratics. Okay, the equation is going to be the parent equation or parent function is going to be y equals x to the 2nd power. And we'll know that we need a quadratic equation if our second difference is the same. Okay, make sure you're writing this down. because you're definitely going to need it during your homework. All right, let's look at what this looks like. Then I'll show you what I mean by second difference. Okay, we're going to start just like we did with linear functions, and we're going to look for the differences. On the x's, it looks like we're adding 1. On the y's, it looks like we're adding 3, but then we're adding 5, but then we're adding 7, 9, 11, 13. Okay, so it looks like I don't have a function here because it's not changing by the same amount every time. This right here is considered your first difference. Remember with our linear equations, that first difference, everything was the same. So that's how we knew it was linear. Well, this one doesn't work that way. So we're going to try again. We're going to find the difference between these numbers now. And because this is the second time that I'm looking for the difference, this is called my second difference. From 3 to 5, looks like I'm adding 2. 5 to 7 adds 2. 7 to 9 adds 2. 9 to 11 adds 2. And 11 to 13 adds 2. If these are all the same on my second difference, then I know that I have to write a quadratic function. Okay, and the parent function for that is y equals x squared. All right, so what I'm going to do first is I'm going to check to see if just plain old y equals x squared will work. If I plug in a 1 squared is 1, so that works, but I better try the next one. 2 squared does equal 4. Okay, I'm going to go way down here. 6 squared does equal 36. So all I need for this one is y equals x squared. That is my quadratic function for this. This is my rule. Okay, that's what I mean by second difference. I have to subtract a second time. All right, our next one is called cubic. And that one, if we were in school making our little booklets, I would have you write it like this. C-U-B-I-C. Because that's what the graph of a cubic function looks like. It makes kind of an S on your graph. And it can go either way. Could go this way, but only one at a time. The equation for that one is y equals x to the third power, or sometimes you might even have to multiply a number with it. So a number times x to the third power. The characteristic is that we're going to have to go all the way out to the third difference this time. Okay, let's try it out. These, luckily they're being really nice to us, and they're having all the x's are just adding 1. This time, to get from 1 to 8, I'm adding 7. 8 to 27 is 19. 27 to 64 is 37. 64 to 125 is 61. And 125 to 216 is 91. Okay, well that was our first difference, so we know it's definitely not linear. If that doesn't work, I'm going to move out to the second difference. 7 to 19 is 12. 19 to 37 is 18. 37 to 61 is 24. And 61 to 91 is 30. Okay, so we know it's not even the second difference, so it's not quadratic. And we're going to try the third difference. 12 to 18 is 6. 18 to 24 is 6. And 24 to 30 is 6. Okay, so third difference tells me that I'm going to have a cubic equation, a cubic function. And we're going to start out just by trying y equals x to the third. So if I plug in my 1's, 1 equals 1 to the third, that one works. Let's try the next one. 8 equals 2 to the third. That actually works too. Let's go to the very bottom. 216 equals 6 to the third. You can double check with a calculator, but that actually works too. So our rule for this table is y equals x to the third power. All right, the last type of nonlinear function that I'm going to show you about is exponential. Okay, and that one I usually like to write like this. Okay, these graphs never touch the axes, but they get as close as possible. And they can go all ways, really. The equation for these is y equals a number to the x power. And the characteristic for this is that it's actually a multiplying difference. Okay, let me show you what that looks like. Okay, so we're going to start by doing the same thing every time. You're always going to check for differences. Okay, so this, nice enough, is adding 1 every time. These, adding 6, adding 18, adding 54, and adding 162. Okay, we know it's not linear. Now, we can go all the way out. We can try a second difference. We can try a third difference. They're not going to work. Only because we happen to know that this is an example of exponential. So what I highly suggest when you're trying to figure out which kind of function this is always check for multiplying first. That'll save you a lot of time. If it's not multiplying, you'll still have to do the differences. But look at this one. If I can already see that to get from 3 to 9, I multiply by 3, and 9 to 27 is multiplied by 3, 27 to 81 is multiplied by 3, and 81 to 243 is multiplied by 3. That just saved me the steps of finding the first 3 differences and not getting anything the same. All right, if I can see that it's a multiplying difference, that is the number that goes in for n. So I will have y equals 3 to the x power. And then I should double check by plugging some numbers in to make sure. So if I take my first set, y is 3. That should equal 3 to the first power. That it does. Okay, if I try this third one, 27 should equal 3 to the third power. That it does. So all I have to have for my function rule is y equals 3 to the x power. Okay, those are the 4 different function rules that you're going to need. And I'm going to show you just a couple examples for you to see what it's going to look like in the book, and then I'll let you work on your own. All right, the book's going to give you things like this. A set of ordered pairs represents a function. What is the rule that represents this function? I suggest that you put it into an XY table just so that you don't miss something. Okay, then like usual, we always start by finding the differences. So x's are adding 1. And I'm going to start by looking for multiplication. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And 16 times 2 is 32. So I know that this has a multiplying difference, which means that it has to be exponential. Okay, the parent function, if you remember, for exponential was y equals n to the x. And my n is these 2's. So y equals 2 to the x power. And then we just want to make sure that that works. If I plug in 2 equals 2 to the first power, that works. 4 equals 2 to the second power, that works. 8 equals 2 to the third power, all of those work. So I know that this is my function rule. All right, this one I already put into a table for us, so I'm going to start by finding differences. X's add 1. 1 times 4 would give me 4, but 4 times 4 doesn't give me 9, so I know it's not exponential. So now I have to look for, here's my first difference. I add 3, I add 5, I add 7, and I add 9. Okay, first difference doesn't work. That means it's not linear. Second difference, add 2, add 2, add 2. Okay, so second difference means that it's going to be quadratic. And the parent function for quadratic is y equals x to the second power. Now I just need to make sure that that works without any additions. Okay, so if I take my first set here, 1 is equal to 1 to the second power. That works. 4 is equal to 2 to the second power. That works. Let's go with the big one here. 25 is equal to 5 to the second power, and that works. So I know all I needed was y equals x to the second power. All right, last one to check on. Which rule could represent the function shown by the table below? Looking for differences. In the x's, I just have +1. In the y's, it looks like I have -1. I'm looking for multiplication. That'd be times -1. But if I do -1 times -1, I don't get -4. So now I'm just looking for differences. I know it's not exponential. Okay, so then from -1 to -4, I subtract 3. Here I subtract 5. And here I subtract 7. Not linear, because my first difference was not the same. Here I would subtract 2, subtract 2, subtract 2, which means it is quadratic, so I can get rid of b right away, because that one has a third power. Now I need to figure out y equals x squared. I have to see if that's enough. Okay, if I plug in my first set, 0 equals 0 squared, yeah, that works. Okay, but if I plug in -1 equals 1 squared, that doesn't work. Okay, because -1 really just equals 1. How can I turn that 1 into a -1? Okay, well, I could either subtract 2, or I could multiply it by a -1. Okay, let's see what works for the others. Let's check this one out. -4 is equal to 2 to the second power. Okay, well, if I did 2 to the second power, I get 4. If I subtracted 2, that isn't going to get me to -4. But if I multiply by -1, that will get me my -4. So that means in my rule here, I just need to make sure I multiply it by -1, and that is going to be my rule. So letter C is the function rule I'm looking for. Okay, I know that this isn't